Hello! Chapter 2 in the Helicopter Flying Handbook, Aerodynamics of Flight. Introduction. This chapter presents aerodynamic fundamentals and the principles as they apply to helicopters. The content relates to flight operations and performance of normal flight tasks. It covers theory and application of aerodynamics for the pilot, whether in flight training or general flight operations. Forces acting on the aircraft. Once a helicopter leaves the ground, it is acted upon by four aerodynamic forces: thrust, drag, lift, and weight. Understanding how these forces work and knowing how to control them with the use of power and flight controls are essential to flight. They are defined as follows. Thrust. The forward force produced by the power plant, propeller, or rotor. It opposes or overcomes the force of drag. As a general rule, it acts parallel to the longitudinal axis. However, this is not always the case, as explained later. Drag. A rearward retarding force caused by disruption of airflow by the wing, rotor, fuselage, and other protruding objects. Drag opposes thrust and acts rearward parallel to the relative wind. Weight. The combined load of the aircraft itself, the crew, the fuel, and the cargo or baggage. Weight pulls the aircraft downward because of the force of gravity. It opposes lift and acts vertically downward through the aircraft's center of gravity. Lift opposes the downward force of weight is produced by the dynamic effect of the air acting on the airfoil and acts perpendicular to the flight path through the center of lift. For a more in-depth explanation of general aerodynamics, refer to the Pilot's Handbook of Aeronautical Knowledge. Lift is generated when an object changes the direction of flow of a fluid or when the fluid is forced to move by the object passing through it. When the object and fluid moves relative to each other and the object turns the fluid flow in a direction perpendicular to that flow, the force required to do this work creates an equal and opposite force, that is lift. The object may be moving through a stationary fluid or the fluid may be flowing past a stationary object. These two are effectively identical as in principle. It is only the frame of reference of the viewer which differs. The lift generated by the airfoil depends on such factors as the speed of the airflow, the density of the air, total area of the segment of the airfoil, and angle of attack between the air and the airfoil. The angle of attack is the angle at which the airfoil meets the oncoming airflow or vice versa. In this case of a helicopter, the object is the rotor blade, the airfoil, and the fluid is the air. Lift is produced when a mass of air is deflected and it always acts perpendicular to the resultant relative wind. A symmetric airfoil must have a positive angle of attack to generate positive lift. At a zero angle of attack, no lift is generated. At a negative angle of attack, negative lift is generated. A cambered or non-symmetrical airfoil may produce positive lift at zero or even small negative angle of attack. The basic concept of lift is simple. However, the details of how the relative movement of air and the airfoil interact to produce the turning action that generates lift are complex. In any case, causing lift, an angle flat plate, revolving cylinder, airfoil, etc., the flow meeting the leading edge of the object is forced to split over and under the object. The sudden change in direction over the object causes the area of low pressure to form behind the leading edge of the upper surface of the object. In turn, due to this pressure gradient and the viscosity of the fluid, the flow over the object is accelerated down along the upper surface of the object. At the same time, the flow forced under the object is rapidly slowed or stagnated, causing an area of high pressure. This also causes the flow to accelerate along the upper surface of the object. The two sections of the fluid each leave the trailing edge of the object with a downward component of momentum producing lift. All right. Bernoulli's Principle. Bernoulli's Principle describes the relationship between internal fluid pressure and fluid velocity. It is a statement of law of conservation of energy and helps explain why an airfoil develops an aerodynamic force. The concept of conservation of energy states energy cannot be created or destroyed, and the amount of energy entering a system must also exit. A simple tube with a constricted portion near the center of its leak illustrates this principle. An example is running water through a garden hose. The massive flow per the unit cross-sectional area of the tube is the mass flow rate. In figure 2.3, the flow into the tube is constant. neither accelerating nor decelerating. Thus, the mass flow rate of the tube must be the same at stations 1, 2, and 3. If the cross-sectional area at any one of these stations or any given point in the tube is reduced, the fluid velocity must increase to maintain a constant mass flow rate to move the same amount of fluid through a smaller area. Fluid speeds up in a direction proportion to the reduction in area. Venturi effect is the term used to describe the phenomenon. Figure 2.4 illustrates what happens to mass flow rate in constricted tube as the dimension of the tube change. Venturi flow. While the amount of total energy within a closed system, the tube, does not change, the form of energy may be altered. Pressure of flowing air may be compared to energy in that the total pressure of flowing air always remains constant unless energy is added or removed. Fluid flow pressure has two components, static and dynamic pressure. Static pressure is the pressure component measured in the flow but not moving with the flow as pressure is measured. Static pressure is also known as the force per unit area acting on a surface. Dynamic pressure of the flow is that component existing as a result of movement of the air. The sum of the two pressures is total pressure. As air flows through the constricted, static pressure decreases as velocity increases. This increases dynamic pressure. Figure 2-5 depicts the bottom half of the constricted area of the tube, which resembles the top half of the veneer foil. Even with the top half of the tube removed, the air still accelerates over the curved area because the upper air layers restrict the flow, just as the top half of the constricted tube did. This acceleration causes decreased static pressure above the curved portion and creates a pressure differential caused by the variation of static and dynamic pressures. Newton's third law. Additional lift is provided by the rotor blade lowering surface as air. Let's go again. Additional lift is provided by the rotor blade's lower surface as air striking the underside is deflected downward. According to Newton's third law of motion, for every action there is an equal and opposite reaction. The air that is deflected downward also produces an upward lifting reaction. Since air is much like water, the explanation for this Since air is much like water, the explanation for this source of lift may be compared to the planing effect of skis on water. The lift that supports the water skis and the skier is the force caused by the impact pressure and the deflection of water from the lower surfaces of the skis. Under most flying conditions, the impact pressure and the deflection of the air from the lower surface of the rotor blade provides a comparatively small percentage of the total lift. The majority of lift is the result of decreased pressure above the blade rather than the increased pressure below it. Normally, weight. Okay, so this would be weight. Normally, weight is thought of as being known fixed values such as weight of the helicopter, fuel, and occupants. To lift the helicopter off the ground vertically, the rotor system must generate enough lift to overcome or offset the total weight of the helicopter and its occupants. Newton's first law states every object in a state of uniform motion tends to remain in that state of motion unless an external force is applied to it. In this case, the object is the helicopter, whether at a hover or on the ground, and the external force applied to it is lift, which is accompanied by the increasing the pitch angle of the main rotor blades. This action forces the helicopter into a state of motion. Without it, the helicopter would either remain on the ground or at a hover. The weight of the helicopter can also be influenced by the aerodynamic loads. When you bank a helicopter while maintaining a constant altitude, the G load or load factor increases. The load factor is the actual load on the rotor blades at any time, divided by the normal load or gross weight of the helicopter and its occupants. Contents. Anytime a helicopter flies in a constant altitude curved flight path, the load supported by the rotor blades is greater than the total weight of the helicopter. The tighter the curved flight path is, the steeper the bank is, the more rapid the flare out or pull out from a dive is, the greater the load supported by the rotor. Therefore, the greater the load factor must be. To overcome this additional load factor, the helicopter must be able to produce more lift. If excess engine power is not available, the helicopter either descends or has to decelerate in order to maintain the same altitude. The load factor and hence apparent gross weight increase is relatively small in banks up to 30 degrees. Even so, under the right set of adverse circumstances, such as high density altitude, turbulent air, high gross weight, and poor pilot technique, sufficient or excess power may not be available to maintain altitude and airspeed. Pilots must take all these factors into consideration throughout the entire flight, from the point of ascending to a hover to landing. Above 30% of bank, the apparent increase in gross weight soars. At 30% of bank or pitch, the apparent increase is only 16%. But at 60, it is twice the load of the wings in the rotor system. For example, if the weight of the helicopter is 1,600 pounds, the weight supported by the rotor disc in a 30% bank at constant altitude would be 1,856 pounds. That would be that 1,600 plus 16%, or 256. Yep. In 60% bank, it would be 3,200 pounds. In an 80-degree bank, it would be almost 6 times as much, or 8,000 pounds. It is important to note that each rotor blade must support a percentage of the gross weight. In a 2-bladed system, each blade of the 1,600-pound helicopter stated above would have to lift 50% of the 800 pounds. If this same helicopter had 3 rotor blades, each blade would have to lift only 33%, or 533 pounds. One additional cause of large load factors is rough or turbulent air. The severe vertical gust produced by turbulence can cause a sudden increase in angle of attack, resulting in increased rotor blade loads that are resisted by the inertia of the helicopter. Each type of the helicopter has its own limitations, which are based on the aircraft's structure, size, and capabilities. Regardless of how much weight one can carry or the engine power that it may have, they are all susceptible to aerodynamic overloading. Unfortunately, if the pilot attempts to push the performance envelope, the consequence can be fatal. Aerodynamic forces affects every movement in a helicopter, whether it is increasing the collective or a steep bank angle. Anticipating results from a particular maneuver or adjustment of a flight control is not good pilot technique. Instead, pilots need to truly understand the capabilities of the helicopter under all the circumstances and plan to never exceed the flight envelope for any situation. Cool. We'll hold off there. That is page 5 of 28. That was the weight. That's starting in the aerodynamics. Yep. That's aerodynamics of flight. We went to weight, page 5 of 28. All right, we're going to move on to drag. No, thrust and drag next. See ya.